Hey everyone, welcome back to Signal Processing with Paul. In this video, what I want to do is explain why and the derivatives of sines and cosines end up having a frequency-dependent term in them and why there's a phase shift involved. So one of the things we saw before is when we trace out the unit circle, according to Euler's expression, we have a sine term that basically traces out the y-axis and a cosine term that traces out the x-axis. And the other thing I want to talk about too is that when we do this, notice how sine and cosine are 90 degrees out of phase. One of the ways in which you can see that this is the case is if I take my cosine term and I put a pi over 2 term, you can see that, cosine of this minus pi over 2 is just a sine term. So what I want to explain is there's no coincidence with the fact that the j-axis is basically a 90-degree rotation of the real axis, and sine and cosine are 90 degrees out of phase, and derivatives are 90 degrees out of phase. So let's go ahead and get started looking at this. So let's start with my red curve, my sine curve. And if we're going to look at the derivative of this curve at each point, let's start by doing this. So basically at point 0, what I have, the derivative here is 1. Because what's going on here is the slope of this point is 1. So I'm going to have a 1 up here. And as I continue moving this point, what I'm going to see as I move it over is when I get to this point, pi over 2, the slope is 0. So I'm going to put a 0. And we can continue tracing this. And it doesn't have to be very difficult to see that what ends up happening is you get a cosine curve, which is a phase shifted version of your sine curve that ends up tracing out the derivative. And hopefully by looking at this, you can convince yourself that this is the case, that basically going from sine, taking a derivative and getting cosine, if you were to do this at each point, it's good exercise, or you don't have to do it at every point, but do it at enough points to convince yourself that, yeah, cosine really is the derivative of sine, and I do see this phase shift. And if we were to take this and do it again, what you would see is another 90-degree shift. So at this point, we would basically be looking at the derivatives here and we get this orange curve. And do it again, you get a purple curve, which is 90 degrees again out of phase. And once again, doing that again, you're going to go back to your sine term. So these are each 90 degrees out of phase. And once again, multiplication by j, this is a 90-degree rotation or a pi over 2 rotation. So should be no surprise here. But now what we want to do is add in a frequency term. So not only do we have sine of just wx, where w is 1, where it doesn't matter, but I want to start varying w and show the relationship between frequency and the derivative. So when I take the derivative of sine of wx, we get cosine of the inside, and then using the chain rule, we multiply it by the derivative of the inside, which of course is just w because we're taking the derivative with respect to x. And what I want you to notice is that as we start increasing our w, because of this term, and this is just me plotting it, what we end up seeing is the derivative starts increasing in amplitude as we increase the frequency. Now, why is this the case? Well, of course, you could say because it's that w there. But if you think about what's going on with this red curve with my original sine, as we increase w, what we're kind of doing is squishing it. And looking at this point where 0 is, my slope is no longer 1. It's because the curve is getting squished and squished and squished. What ends up happening is that slope or that rate of change becomes much, much higher. And likewise, as I go below 1, what ends up happening is it starts decreasing and becoming less and less than 1. So one of the things that should make sense is as you start increasing the frequency, you have a higher rate of change, and as a result, your derivative is going to be much higher in amplitude. So when we start writing things as a function of frequency or as a function of sines and cosines, we should expect those sines and cosines that have a higher frequency when we apply a derivative operator to be amplified, whereas those that have lower frequencies to be attenuated or even decreased down. Now let's do this in the opposite direction. So let's look at the integral. So at this point I'm going to do is I'm going to start with this blue curve, which is cosine of wx. And what I'm going to do is look at the integral of this, which is sine of wx divided by w. Once again, just due to the chain rule. And now I want to show what happens as we vary w. Notice how in this case, we actually see a phase shift 90 degrees in the other direction. And what happens as we increase w? Well, because we're dividing by w, higher frequency terms actually get decreased in amplitude. Now, why is this? Well, as we increase the frequency, we're squishing down our original function, and as a result, this area under the curve actually becomes smaller and smaller, and that's why the amplitude of sine of wx over w ends up going down. So when we take an integral, unlike the derivative or the opposite of the derivative, which should make sense because integrals and derivatives are opposite, what we end up seeing is an actual attenuation of high frequency terms. And on the other hand, when we decrease our frequency below 1, what we end up seeing is these higher frequency terms, these lower frequency terms end up getting larger and larger. And once again, that is because we are increasing the period or decreasing the frequency. So we have much more area under the curve that we're accumulating starting at 0. So once again, this inverse relationship between derivatives and integrals and how they will attenuate or accentuate lower or higher frequencies is really important to understand. Now, most of the time, we are not going to be using sines and cosines. We're going to be using complex exponentials, and then we just project them to a sine and cosine when it's convenient for us. This makes the math much easier, and rather than having to worry about where the minus sign goes, you just drop down a 1 over j2 pi or multiply by j2 pi in the case of an integral or a derivative, respectively. But hopefully this gives you an intuitive understanding of the relationship between derivatives, integrals, phase shifts, and amplitude based on frequency. Thanks for watching.